Okay, that's me back. I think we'll get started in a few moments. Anybody got some general questions before we get started on the Lagrange method of optimizing functions?
Yeah, Professor, did you record your Wednesday meeting? Was that for us?
Yes, I did actually. I believe I put it online. I'm not quite sure where I put it online, but I'm pretty sure. I'll take a note just to make sure that I did that.
So yeah, if you could send that out, because I missed it on Wednesday. I didn't see your email until yesterday morning.
Okay, so I'll check that out for 264. Any other questions?
I have a question about the double derivative test.
The double derivative test.
Just,
okay. I know what you're calling it now, right? The D test.
Okay. Yeah, the D test. So just, I was curious as to why it's the double derivative of X that kind of determines if it's going to be a max or a min. Like,
actually,
just wondering how that works. It
you
doesn't matter.
You could have done the Y and it'd have the same effect.
Okay.
But they had to pick one. It was kind of pointless to do it to both when one would have told you the answer.
Okay.
Yeah, technically speaking, the book's been a bit generous and the questions are being a bit generous because of saying if the second derivative is negative, and you know in negative, let me move my hands out a little bit here. Yeah, you know if it's negative, what's going to happen is that you're going to have that shape.
Right.
Right. Now, if you're cutting something parallel to the x-axis, you can imagine that if you saw that hell shape, you'd be looking at a maximum. But if you turned 90 degrees and you cut it in the y-axis, you'd see the same thing. Right. So technically, they only needed to do one. So I think x came before y, so that's why they got their job.
All right.
Right. You know how when they say d is less than 0, you're in trouble?
Right.
What the book says is that that is technically going to be a saddle point because every question they gave you, it is a saddle point. But there's a nuance there. Technically, you don't know what's going on there. The vast majority of the time, it is a saddle point, so we'll just go with the flow and say that it is. But technically, there are some weird functions out there. An analogy. Can you remember when you did the second derivative test in Calc 1? Basically, the first derivative is 0, told you where to look. And then if the second derivative was positive, it meant you were concave up, so you had the minimum. And if it was negative, it was down. But what happened when the second derivative was equal to 0? It wasn't guaranteed to be, I'm going to have to go high. It wasn't guaranteed to be a point of inflection, was it? Although very often it was, right? It was possible for the second derivative to be 0 and still have a local max, strangely enough. Well, that same thing is true in the 3D world. But for the sake of simplicity, they're pretending it's not. So I just want you to make sure that, yep, if it's negative, just call it a saddle point and go with the flow. But in reality, 99.9% of the time, that will be totally correct. But there are some weird functions in the world. When you go into 3D, the weirdness can be even stranger. When it's only a graph in 2D, there's not so many weird things that a curve can do. But you can imagine when you add another dimension, you can imagine you got a piece of paper and gave it a really weird twist. Right, it's a flat piece of paper and you gave it a weird twist. Can you imagine there can be some really weird looking curvatures inside that 3D space now? And some of the D less than zeros are telling you that weird thing is happening. Anything else?
Piggybacking on what Jackson said in the chat. So when D is equal to 0, like what does that actually look like on the graph?
And like how do we do to because you said like it could be either concave, it could be either a max or a minimum or neither. Like the book doesn't really talk about what to do. It just says that it doesn't tell you exactly.
Yeah, it's another the mysteries of 3D. The D test, as I'm going to call it, right? Just because it reminds me there's a D in the formula, is going to be good. You're not going to be hit by trick questions where D equals 0 in the test, right? You're not. I don't think that. I've looked through all the homework, at least 3/4 of it, and I haven't seen any D equals 0s happening. So we won't be too worried about that. We just put that down as a, yeah, you know, you do what you do, and hopefully nothing comes of that. If you wanted to say, well, what would I do in real life if I had a surface here and I did the secondary, you know, the D test on it, and I got a D equals 0, you know what I would do? I would just look at it in algebra, that one, GeoBra, whatever it's called, the 3D thing, and say, oh, that's weird looking. Okay, that's what it is. It might not be weird looking. It might just be a saddle point, just a weird version of it. And you'll say, okay, then that's what's happening. Anything else? Any other questions? Right. Let me make sure that I've set up something before I go any further. Evidently, come on, where are you? There you are. You probably can't see this, but you will see it in a few moments. Okay, let's go back in. Oh, I've got some latecomers. I better let them in. Okay, hi, Justin. Okay, so let me do a screen share. And we'll go into it should be here. Right, have you all seen, I had a look at this GeoBra thing, right? This guy here. So let's just suppose that you were interested, and it's a good way to check your functions, although I have to be careful about the syntax. So I kind of got it back to front. So if you take a function and you just wanted to know what it looked like, there's x squared, take away. Actually, let's leave that one for a minute because it's kind of interesting. This is what f of xy equals x squared minus y looks like. Are you all seeing the GeoBra that I have in front of me?
Yeah.
Good, okay. So if you think of f of xy as being the z coordinate, and the z, the height, is x squared minus y. I try and think of xy as the floor, and the function as being how high up it is, right? Plus or minus, could be down. Now, if you look at this particular shape here, what's kind of nice about this software is if you hold your mouse around it, you can actually get a kind of feel for it. You know, without too much guessing, do you know that would be a pretty good model of the front of the ship, wouldn't it? Now, I don't think that's the best model in the world, but people who are into this, couldn't you tweak this and make it a bit shallower, a bit steeper, a bit narrower, and find out what would be a good surface for the front of a ship? I mean, you can imagine people playing about with this thing. Now, if I go back to this fella here and make it an x squared, and I click out and I rotate this fella, if you haven't really got a good idea, because I think last time I'm playing about with my hands, can you see what a saddle point looks like? You notice you're coming down this way, that looks like that you're at the bottom of a hill, which you are from that person's perspective. But if you orientate it a different way, can you see that if you were coming in, stop moving. If you were coming in from this side, wouldn't this point represent a maximum? So can you think of a saddle point as like a, in the 2D world, isn't it like a point of inflection? So if we looking at those guys, that's what one of those fellas look like. If I put this one up, there's a very boring local minimum, right? And if you wanted to see what a boring, hopefully this will work, a boring local maximum would look like. There you go. So as you're going through some of these questions, you might want to plug the guy into GeoBra. If you do the math in the calc and it says there's a local min at this place and that place and a local max at that place, you put this in and go and look for it. Now, GeoBra doesn't know what your scale is, so if you kind of curl the middle mouse, in my case it's a wheel, if you turn it one way or if you turn it the other way, it kind of zooms in. It's really zooming in now, right? But sometimes you have to zoom out a little bit to see the whole picture, and sometimes you zoom in if you're only focusing on one little thing. Now, the other thing I want to show you, and then we'll start some questions, is here. You all know, or you should know, that your test is due on Sunday, and it's some of you are not maybe 100% sure how this is going to work. When you go to your WebAssign, it's not there yet. On Sunday morning, it's going to appear. And when you want to do it, will you make sure that you click on it only when you're ready to start? Because it's going to be a one-shot deal. Once you enter it, you're in the test, right? So don't, oh, I wonder what it's like, because then you're going to say, I'm not ready. Now, once you're finished with it, you're going to upload it. So let's show you what's going to look like. Do you see this guy says working for test 1 due on Sunday? When you finish your test, you'll have some stuff. Now, there are all sorts of ways of doing this. I've gave you a program that you can use, and it's free. And let's find out where the heck it is. There it is, how to get cam scanner. So you can use that. And basically, you take your phone, you take a picture, it converts it into PDUs, you join them together as a single file, and you send me. So once you've done all that, you'll then click on this fella. And I've given you a little video here that will show you what the details are. But essentially, all you do is, there's a thing up here says like upload. You click on it. A window is going to appear. And in that window, it will say upload file. You have it in your desktop. You pick it. You say, open this guy, it brings it up and it's done. Now, if you change your mind, or if you, oh, I forgot a page, I just realized there was another page of working, you can just load it up a second time with the same name, and it will rub it out, and I'll only have one. Okay, so have that, watch that little video, and it's hopefully pretty obvious what you need. We're good. Right. Now, is there any specific questions in especially Lagrange, because that's what I want to focus on today? Otherwise, I've got a whole load of solutions I want to go over, as many as at least I can, to help you with your homework and to get you ready.
Could we do 14.7 questions after, or would you rather?
We could do it now if you want. The order doesn't matter to me. So 14.7? Yeah. Do you want 14? Oh, I got you. You want a max min problem first? Yeah, let's do that first.
Okay.
In 14.7, which one was causing you issues?
Can we start with, well, I had a couple written down, but.
Well, we'll do, maybe if I do one that will cover both issues.
Okay.
What you got?
I think we should just go with 12. 12
okay.
Was, yeah.
12's a stinker.
Got bounded by the different lines.
Right, now the one I'm looking at here says x squared plus y squared plus x squared y plus 9. Is that the same kind of question?
Yep, same kind of question.
Right, and what you've got here is that you've got a restriction here that basically says, I want to find the absolute max or min of this function, but you can only pick x's and y's in this range here, right? That's the one?
That's right.
Okay, so what's that, 12? Let me see what I can do here for you. Okay, I got the guy. So here we go. Click on this fella. Okay. Okay, what the heck have I gone and done? I've got a miniature version of me, and I want a full version of me. And I don't want to hit the wrong button in case I screw up. Oh, here we go. It's just being awkward because it can. I want to do full screen. And evidently I don't have that capacity right now. So why? I need to, there we go, shooting space. You gotta have eyes everywhere. There's a little tag up the top that I needed to click. Right. So anyway, I needed to go out so I can go back in. It's just the way this darn thing works. And the question you're talking about, I believe, is this one here, right?
Yep.
So let me talk through this question. Although all the details are here, I'll try and give you. Essentially, you've got a function which you're going to find the absolute max and min for, and it's under certain constraints. So the first thing that you're going to do is find all the critical points. So ignore this bit D and just go for the usual places, which is what we call the critical numbers, the critical points. So if you take your function, which is this guy, and you do the partial derivative with x, and you do a partial derivative with y, here are the two equations that you set to 0. Now, the thing that makes these questions so awkward is that very often the partial derivatives of x and y, the functions you get aren't just 4x plus y and 2x minus 7. They're weird things, and you have to just develop strategies for doing it. This particular strategy is that I noticed that since these two are the same, if I take this first equation and subtract the second, they kill each other off, and you're left with this relationship, which eventually tells us, oh, that x equals y. Well, if x is equals y, I can then go back to this one here, for instance, or I could have done that one if I wanted, I guess, and solve for it. And when I solve for it, I find out x is 0 and x is -1. And we understand those two guys as essentially our critical places. Now, when you do x is 0, you get y is 0, which is the origin. And if you do x is -1, y, of course, is the same value, so it's also -1. Now, these 2 points could be the biggest answer in the curve, right? The absolute max. It could be the smallest one, the absolute min. But before I even check that, I should look at these two and now figure out, is it subject to what we call this constraint? And the good news is that both of these points work. You can imagine the origin. It's definitely got an absolute value of x less than 1 and a y that's less than 1. And these two guys just made it on the fringes, but they still count. So my candidates right now for the absolute maximum are look at 0, 0, which gives me an answer of 6, or look at -1, -1, which I believe gives you an answer of 7, but you might want to check my calculations there. Yes, it is, right. So that's that done. Now we get the tricky part. What about this D thing? Right, this guy here. Well, there's a picture of what it looks like. Can you imagine you drew absolute value of x between 1 and -1 and y between -1 and 1? You end up with a box and everything that could be inside it. We've already taken care of the everybody inside it. That's these guys up here. So what I'm now going to do is I'm going to try and find what's happening along these red lines. So essentially you take your function, your f of x, y, and you look at what's its values like when you only pick points, say, along this line here. or you only choose points along this line here. So for instance, if I take the line x equals 1, which is this guy here, line L1, then what do I know about that? Well, I know x is 1. So does it not make f of xy, which is this guy, really the same thing as f of y, 1y? Because if x is 1, these x's here are all being 1. And so what you got now is that when you look at values along this value here, this slice here, that's what it's equal to. Whatever y squared plus y plus 6 is. And I can tell you, because I know basically enough about quadratics in the world, that that's going to happen at y equals -1/2. And can you tell why that is? Do you notice that that's going to be a quadratic, and therefore the vertex is going to be the minimum location? And so what I've now managed to do is that if you pick values only between here and here, that's x equals 1, the biggest or smallest answer you're going to get is going to happen at y equals -1/2. So that gives me a place to look, 1 -1/2. And when I did this, I got 27/4. Now, if you go and you do it through all the other lines, you find out that when you pick, for instance, the line L2 or this one down L4, where the y value is -1, you get an answer of 9. And when you pick the other guy at the side here, line L3, you find that the best answer you get is 27/4. So I look at all my choices. At the origin, the function had a value of 6. At -1, -1, it was 7. At this guy here, the best answer it got was what, 6 1/4, another 6 1/4, and a 9. So out of that entire set, the smallest answer we ever got was at the origin, and it had a value of 6. So that's its absolute minimum. And then we managed to get 2 locations. They're basically at the corners there and there, where the value of the function was 9. So that's quite a unique question, because you're doing the usual stuff, which is just find out where these guys are, max and mins, and go for it. But now you're not looking for local max and mins. You're actually being asked to find absolute max and mins, which are not quite the same thing. All the solving of this does now is tell you places to look. It doesn't tell you that they're the best answers or the worst answers. But you know, the math says that they're going to exist in one of these locations. And then you go and you look at the constraint guy and you figure out what's going to make, what's the biggest and smallest happens within the edges of the shape in this case.
So we're kind of like doing a trace on our boundary.
Yeah, and on that trace, you're just finding the height of the curve.
Okay.
So you imagine that's the floor, but if you took that floor and project it upwards to the surface, you see that you would see would be a trace on the curved surface. And at some places it would be higher, and in others it would be lower.
Okay, yeah.
It's, it takes, I mean, we're not 3D people in math generally. You spent your entire mathematics career, for the most part anyway, isn't it, dealing with 2-dimensional curves, f of x's. And so now we're projecting that information and trying to deal with it in a lot of ways in a much more realistic way. If you think about it, 3-dimensional functions are probably more interesting as well.
Yes.
Okay.
Real quick, just so that I can see what's going on this. So you have your f1 of y, and you get it down to y squared plus y plus 6.
Yep.
And you're just using quadratic formula to figure out y is equal to 1 or -1/2.
Yeah, in this case, it's what, -1/2.
Okay.
So x is 1 and -1/2 is the only place that you need to worry about, because that place, something extreme is going to happen, either extremely big or extremely small in that little piece of the world. And then you take all your big and smalls. There's a lot to choose from, right?
Uh-huh.
And whatever place gives you the ultimate biggest answer out of all the set, absolute max. And the places it happens, which is in this case here and here. And the place, the smallest answer that you get is your absolute min.
I have a quick question about what you're showing us right now.
Yeah.
It looks like your first instance of f of 1 comma y has 1 squared, and then the 1 squared seems to run off in the next line down. I'm just kind of wondering where that 1 would go.
One. Ooh. Interesting.
Yeah, it looked like it should be y squared plus y plus 7.
Yeah, it should be. It should be a 7. The good news, it didn't affect the answer because it's still going to happen at this point.
Gotcha.
Now, when I plug in the -1/2 guy, does it change the answer? 6 1/4. This is still the final answer, but that guy, I'm going to have to go back and do my usual, figure out what happened. The process is right, I just can't count. And these two answers are still correct. That may alter a little bit, but it's not going to beat the 9, so it won't matter.
Gotcha. I just wanted to make sure that I wasn't missing something.
No, when you watch me or you get used to me, you'll know I'm just bad at counting. This guy is actually online, so I'm taking a little note to fix that or to look at what it is. That's number, what's it in my list? It's number 13 in 11.7. Okay, are we good?
Yeah.
Right, can we, these, unfortunately, no way of, yeah, sorry. Let me stop sharing for a second. Okay, what was the question? I thought someone made a noise and it was me cutting you off before you had a chance to say something. I guess we're good. Okay, let's go back now. I'll share this fella. Who's this guy? Oh yeah, Lagrange multipliers. Right, I've got all these guys online as well. So when you go and look at your Canvas, go to the place that says something like online help. That link is on the front page and you'll get these. And bearing in mind what just happened a few moments ago, the process will be correct, but sometimes my counting's not brilliant. Okay, let's start with this fella. French guy Lagrange came up with a technique for finding absolute max and mins of a function when it's subject to a constraint. So it's very similar to those questions. Remember the box one we did a minute ago? Very similar to them, but what they do now is that it's formalized in a very algebraic way. It's a bit like magic, but the cool thing about this piece of magic is it works. It tells you what you need. So imagine you have a function x squared minus y squared, and you're going to look at what's the maximum and minimum value of that surface. So can you imagine that might be, I don't know, it could be anything. It could be like somebody's hat, you know, like a surface perhaps, or it could be a saddle point shape, whatever it is. But now you're going to do it subject to this constraint. Now this is a very three-dimensional kind of thing. So can you imagine on the floor, you've drawn all the x and y points who have the relationship that x squared plus y squared equals 1. Do you recognize that it'd be a circle on the floor, radius 1, center of the origin, right? Now, can you imagine that circle going upwards until it meets the surface of f of xy? Now, when it does that, because the surface of f of xy goes up and down, if you looked at it vertically above, you just see a circle. But if you looked at it kind of side on, you'd see that that circle would actually ripple up and down as it went along the surface. So can you imagine on that very distinct curve in 3D, there are certain places where it's higher up, and that's the absolute max, and there's other places on that curve where it's lower down. So that's what you're solving. You're trying to find places on the curve that are subject to this constraint. Now here's it's just a theory. The gradient of fxy, you set it equal to lambda times the gradient of g. You take your constraint function and typically you write it down like this equals 0. Now, when you take this and you do the partial derivative of x and y, and then lambda, the partial derivative of g, x and y, this is what you end up with. This fella here. Then what happens? Well, our job is to solve this system of equations. There are technically 3 of them. This vector is equal to that one. So this guy is equal to that. That's the one I'm calling equation 1. This guy is equal to that. That's the one I'm going to call equation 2. And I prefer this version of the constraint rather than that one, but both are correct. And I will make that my 3rd one. So your 3rd equation is always going to be a constraint, and the other equations, sometimes there are 2 or 3 of them, come from here. Now, if you look at this system of equations, it really does get messy. You've got a variable called x, you've got a variable called y, and you've got a 3rd variable called lambda. And our job is to find out values of x and y where these 3 things are all true at the same time. The textbook does it a way that I don't like, and if you like the way the textbook does it, then do it that way. But I'm just going to show you the way I think is a little bit easier. And it's just a difference in the algebra of solving that. That's all it is. So the first thing you always do, or I always tend to do in these questions, is let's test what would happen if lambda equals 0. Well, if lambda equals 0, wouldn't this line eventually say, right, that x is 0? Technically, 2x equals that, but it's still x equals 0. And if you looked at this equation here, you'd end up with what? Negative 2y equals 0, so y equals 0. We go with that. So if lambda is 0, and you want to solve this system of equations, and we're making the assumption that it is 0. If you did that, wouldn't you come up with a solution that for that to be true for all 3 equations, x would need to be 0 and y would need to be 0? But if that was true, 0 squared plus 0 squared would have to equal 1. So what that is telling me is that that point there is no good. Lambda equals 0 did not give me a viable solution. So what I can then do is I then move on to phase 2. Let's assume lambda is not 0. We've already tested it 0. Let's say whatever I know about it, which is very little, let's pretend it's not 0 now. And then I do this little trick. If you take equation 1 and you divide it by equation 2, do you see these 2 guys go here? These 2 guys go here. Now, superficially, you might think that's a weird thing to do, but here's its one big advantage to this technique compared to the way the book does it is. Do you notice that when you do equation 1 by equation 2, aren't you always going to eliminate the lambdas? They're just going to go away, right? They're going to cancel out. Now, if you tidy this fella up, actually, I should have tidied up more, but it still works. Can you see that you get a cross multiply? 4xy equals 0. And what does that give me? Well, it gives me a relationship that says that if lambda is not equal to 0, the only way this system of equations is going to work is if that 4xy is 0. Now that generates 2 possible roots. Let's go for x equals 0. Just x equals 0, nothing else. Now, if you make x equals 0 and you substitute it into this equation, do you see that you end up getting 2 values of y that work with it? That gives me 2 places to look now, at 0, 1 and 0, negative 1. And then if you choose that one as 0 and you plug it into the constraint equation, because that's what you do, you find out that you now have 2 choices with x, which generates 2 more points. Now you might say, but what happens if I make x equals 0 and y equals 0? Well, can you see that that's actually been taken care of earlier on it gives you a non-usable point. So there's only 4 places that you need to look. There, 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 and there. Now, do you see that this particular technique doesn't use the D method? You don't need to find second derivatives or the values of D or anything like that, right? You just don't. It takes a totally different approach. So at these 4 places, you evaluate the function. And in this particular case, 2 of them are identical and are the lowest, so those are the absolute minimums, and 2 of them are 1s, and they're the absolute maximum. But can you imagine in another world, this was 1, second one was 2, that was 3, and that was 4. Well, if that did happen, the guy at the top, the 1, would be the absolute minimum, and the biggest number at the end would be the absolute maximum. So that is a very simple version of this Lagrange multiplier method. But every single question that is in that list that we unfortunately don't have time to go through, but hopefully you can go online and canvas and find the rest, you're going to find that pretty much I go through that same process. So if you get used to the process, the magic, if you like, you're going to be able to figure out at the end this problem. What's the absolute max and min of that function with a given constraint? Do we have any questions? Or have I overwhelmed you with too much information in one go?
So if you're gonna summarize the steps on this, would you say start with gradient vectors?
Yep.
And then I guess what is the lambda doesn't really seem to be doing a lot in this case, but
the method, yeah, the lambda is quite interesting. The way this method works, or why it works, is quite interesting. But basically, it uses the contour plots of both functions. So if you imagine f of x, y, a contour plot, you know, it's like points of equal height, and you draw it on a 2D piece of paper, and it gives you kind of like a map view of what the surface would look like. And then on that, you put your kind of circle guy. And then this little lambda fella is like, what would you describe it? It's like a dilation factor. So you take the circle and you kind of move it around, and as you move it around, it goes hunting for places where heights happen that are important. Now, for instance, see when you make lambda equal 0, the first situation. See that guy there? Do you know what I'm doing is I'm just finding the good old-fashioned local max and mins of that function. So when you shrink the thing down to nothing, what you're doing is you're saying, and the constraint doesn't matter at that point, what would be the local max and min? And then later on you test it against the constraint. But when you do it, all the other lambdas are basically like stretching of the constraint function to find what would the lambda have to be for that function to touch this curve at a max or a min. I don't think that was a very good explanation, but you know, it's the best I can give you. If you go into deeper math, you'll get into some really cool stuff, and you'll find out why these things are the way they are, essentially. So back to what you said, right? You use the gradients to generate 3 equations. That's the first step, right? So here is f, here is g. Set up this, essentially it's a vector equation with gradients, right? Set it up to get these 3 equations. You always test lambda equals 0 to see if it gives you a point that you can use. And then you can say lambda not 0. And you might say, well, why don't I even bother with that? Why don't I just jump straight into this line here? Well, here's the reason. If lambda was 0, would I be able to divide these 2 equations? Well, no. Right. So I test lambda 0 on its own, and then I say, I'm now making the assumption that lambda is not 0, and now I can do the other piece of algebra. And this other piece of algebra is just get rid of the lambdas, and try and get a relationship in the x's and y's so that eventually you can either, in this case, replace one of them with a number, or sometimes, do you know what you replace is? You say, oh, x has to equal 2y, or x has to equal y cubed, and you use that substitution on the constraint equation to come up with some numbers that work. Now, once you've found all the numbers, all the points that work, you evaluate them, and whoever's the biggest answer is your absolute max, and whatever ones give you the smallest is your absolute min. Are we good? Okay.
Yeah.
Yeah. So, yes.
Maybe just jumping ahead. I saw a example of the Lagrange where they instead solved for lambda just using one of the equations generated and then substituted.
The lambda method is a totally different method for doing the same job.
Okay.
So what you're going to have to do is you're going to have to look at my solutions where I do it my way. I'll call it my way. I'm sure someone else invented it before me, right? Doing it my way. And then you can look at the textbook and you can look at how they do it with the lambda. And then one of them is going to make more sense to your brain or easier for you to do. And I suggest you just go that flow. It's not a good idea for me to show you two different methods because I think that just adds to your workload. Okay. I'm picking this method only because I believe in the way my brain works is that it's easier. But it's not necessarily the way your brain works. And you may say, no, I kind of like that way that they did the lambda first and used the lambda to get the answers, instead of making the lambdas go away and then do, you know, something with the x's and y's instead, which is my method. Okay. But, you know, they both work and they both give you the same answer. So, hey, pick what you like.
All right.
Okay, someone else got a question? Do you want me to just go and pick another one then and talk through it?
That would probably be good.
Okay, we'll do it that way then. I'll just return to the sharing. According, and it's fingers crossed here, according to the little thing on the left there, this is actually being recorded and it should have sound. Who knows? But that's what I'm going for. Okay, here's Lagrange coming up. I tell you what, I'm going to zoom through one and then I'll concentrate on another one because I want to try and get as much out of our time as we can. So here's another one. This is quite early on. I believe this is similar to question 4 in the homework. All the ones in this sheet are just taking, for the most part, taking homework questions and doing them. So when you come and do your homework, you'll probably see very similar versions, but you know that'll be 24 and that'll be 90 or something. Okay, so the function we've got is xy. And the constraint is this one here. You just have to trust me on this. Do you know that's an ellipse, center of the origin? So here goes. You set up the deltas, right? These guys here, the gradient of f is equal to lambda, the gradient of y. When you differentiate this fellow with respect to x, you get y. And when you differentiate this fellow with respect to y, you get x. That's not really a mistake. It is what it is. And hopefully this guy is correct. Yes. So from this line here, we get equation 1 and equation 2. You can see the y equals this guy and the x equals that guy. And then the constraint is your third equation. So it's pretty similar to what we did the last time, right? Equation 1, equation 2, equation 3. Just like I did the last time, I start with test equals 0, lambda equals 0. So you plug in 0 and you get, well, if lambda is 0, you see y would be nothing. If lambda is 0, x would be nothing. But if you plug 0 and 0 into equation 3, it doesn't work. So guess what? There's another example of we can't use it. There will be times, trust me, it does happen, that you put lambda equals 0 in and you get a number, you get a point that can be used, in which case that'll join my list of possible answers. You do the divisions and you cancel them out and you do a little cross multiply, and I get this relationship, which means I can replace y squared by 49x squared. So instead of this guy, I can replace that guy by this, which gives me 98x squared, which gives me those two guys. And now if I substitute x equals -1 into the constraint function, it allows me to find out what the y's would be. So when x is -1, y is this guy. When x is -1, y could be this guy. And the other solution was 1. So plug 1 into the constraint. So basically, once you know what an x is, you go to the constraint function and you figure out what the y would be to make that work. And so what we've got are 1, 2, 3, 4 points that we know we can use. When you evaluate the function, 2 of them are negative, so they're absolute minimums. 2 of them are quite big and positive, so those 2 are the absolute maximums. Now, I'm zooming through that one, but do you get the flow for how this works? 3 equations, lambda 0, see if you can use it, lambda not 0, divide equation 1 and 2, figure out what the connection between x and y is if you can make one happen, and off you go and do the rest.
This is surprisingly not gross. I figured it would be a lot more gross when you start introducing other values like lambda and stuff. But is there a world where, I think you may have mentioned it too, where lambda isn't just immediately destroyed by dividing those first two equations?
Well, the good news is no, there is no world, and I'll tell you why. Do you notice how this lambda goes here? Right? Do you know all of them have lambdas in them? So each one here will only have a single lambda. So when you divide it, they always kill each other off.
Yeah, that's why I was making sure, is because it looked like algebraically that could never occur. I was just making sure there wasn't some sort of weird case for it.
Yeah, which is one of the reasons I like this method. If you look at the, I'm trying to sell what's not my method, but this method. If you do the other method where you try and solve for lambda, it's not as consistent a process, because depends on what you get, how you're going to get rid of lambda, right? Because in some cases you're going to get rid of it by a division process, and others you're going to make it happen by making 2 things equal, and collecting like, there are just all sorts of nuances in that technique. One of the reasons I like this technique is it's kind of standard for most questions, and if you can figure out how this process works, all that's going to happen is this guy will change, that constraint will change, but the process will not change. And that just makes life, in my brain anyway, a little bit easier to deal with.
Yeah, exactly. Thanks.
Right, so let's get this guy. Unfortunately, this is going to be our last guy. Well, I can kind of, if you want to, and your time is valuable, if you want to, I can run over a little bit, but I will have to stop maybe about 20 past 12 because I have another Zoom meeting to get ready for. If you're happy at the end of this question, then feel free. Your time is valuable, so if you think, yeah, I've got what I want, just leave and get on with your homework and do what you're doing. But we should be able to have 2 questions done on this time. So let's see what we've got. The difference here is that we've now got this function. It's not the horriblest function in the world. In fact, it's really quite nice. But what is different is, do you know it says f, x, y, and z? When it was f of x, y, do you know you can draw that picture in GeoBra and it's a surface in a 3D world? Here's the stuff that's going to hurt your brain. This is a 4th dimensional object. In fact, it's a surface in 4 dimensions. Because in x, y, and z, they're all variables. And then the 4th variable, which I don't know, I'll call it w, right, is made up of these guys. So forget about visualizing it. Your brain can't handle it. 4th dimension is not a place to go. So because of that, you have to trust the math now. right? And if someone says to you, what is the biggest and smallest value that this expression can equal when you're only allowed to pick values of x that have this result here, right? This is your constraint. Now, if you want to imagine what that would be, is this thing here is actually an ellipsoid in 3D. So in fourth dimensional space, they've got a three-dimensional ellipsoid, and you're only looking for points on its surface. Do you see how that hurts your brain? So what you do instead is, I now have a math question. How do I find the biggest value for that when the x, y's, and z's have to equal this? So good news is, you just extend the process. Here's the gradient of x, y, z, and it's lambda, the gradient of the constraint function. You differentiate this, you get 6. You differentiate this, you get 6. And you differentiate this, you get 2. If you differentiate this, you get 6x, with respect to x at least, 6y, and 4z. That number doesn't really matter. And this is the line that we get. So it's really the same idea, just a bigger picture, right? A bit more complicated. So what we're now going to have are 4 equations. If you match this with this, you get equation 1. If you match the second term with this one, you get equation 2. And if you match this fella with this one, you get equation 3. And remember, your constraint function is always your last equation. So now we have a system of equations with 4 variables, x, y, z, and lambda. And they're not even linear equations, which you could have solved if it was 250, right? You know, linear algebra allows you to solve matrices and so on. This stuff is, you know, you get what you get. This time it came out really nice, but can you imagine if x, y, z was really messy? These guys here and these guys here especially would be much messier. But here goes. I'm going to stick to my technique. Test lambda is 0. What kind of points do you get out of this system equation, right? What x, y, z do you get if you make lambda 0? Well, if you make lambda 0, can you see immediately you get a problem? 6 will have to equal 0. Ain't going to happen. That means lambda doesn't generate any meaningful solution. In fact, it doesn't even generate a 0, 0, 0, which you can then tell doesn't work. It doesn't even tell you a number, because nothing in the universe that's a real number, at least, or any number, is going to make that work. So now we move on to assume that it's not 0. Well, it's an adaptation, a kind of extension of the technique. If you take equation 1 and equation 2 and you divide them, you get 6 on the top and the bottom, and you get these two guys. Do you see that they cancel out quite a lot? And a little cross multiply. You now know that y is going to equal x. Whatever it is, you know, whatever x is, y is going to be the same number. Okay, I can live with that. Now, if you take equation 1 and equation 3, you get a 6 on the top, 2 on the bottom. You get this guy on the top, you get that guy on the bottom. You do a little cross cancelling followed by cross multiplying, and you get z is a half x. Oh, so y will be equal to x. Z is going to be a half x. That's actually helpful, because when you look at the constraint function that has x, y's, and z's, can't I replace the y with x? Can't I replace the z with a half x? So what I've been able to do is take my constraint function and reduce it to an equation that only has x's in it. And I get that x can only have 2 solutions that will work, plus and minus 2. So if I make x 2, for instance, won't y, because it's equal to x, be 2? And won't z, because it's half of what x is 1? Hey, there's one of the places, one of the only places I need to look. Now, what about negative 2? Negative 2, negative 2, half of negative 2. So do you see that we now only have 2 points? You couldn't visualize that. You couldn't draw a picture of that. There is no software in the world that I know of that does 4-dimensional. So do you see this as pure math? It's the technique, the magic, if you like, has figured out where you need to look. Now, since there's only two places to look, that's here and here, I now evaluate the function, right, the 6xyz guy, and I get negative 26. And when I do it with the 221, I get positive 26. So we have answered the question. And to remind you what the question is, what's the biggest value that guy can be? And the answer is 26. Where will it happen? It will happen when x is 2, y is 2, and z is 1. What's the minimum value this is ever going to be? Oh, it's going to be negative 26. And where will that happen? When x is negative 2, y is negative 2, and z is negative 1. Now, isn't that really kind of amazing that this Lagrange multiplier technique is able to solve such a complicated question? I mean, before this fella figured this out, I'm not even sure how you could do it. You can't even draw the thing. I mean, I guess you could just write down as many numbers as you know that are true for this. And for every single one of the x, y's, and z's, plug it in here. And whenever you got to the biggest answer, that would be it. And that would only be an estimate, wouldn't it? I mean, because isn't there an infinite number of x, y's, and z that this is true for? But thankfully, we don't do it. But once that has been figured out, do you know that you can do a 20-dimensional function? Can you imagine f being a function of x, y, z, and then you run out of variables? Horrible thing. Subject to a 10th dimensional constraint. Now, the only people in the world that I could even imagine going there are the like 2 people in the world who do string theory and do the math of it, because I believe, at least what I read, is that in string theory, you know, it's a way of looking at the way the universe works. You need 11-dimensional space. So can you imagine some poor soul working with a function with 11 dimensions, and then you put certain constraints on it and try and solve what that would look like? You only need to worry about 2 and 3, which makes your life a lot nicer. Right, any questions about this one?
Conceptual questions.
Sure, go for it.
So we have a function that's just some shape, and then we have a function that is some constraint.
Yeah.
Which is just, looks like that's just another shape. And we're looking at the gradients of them. And when we set each component of the gradient that's in the same variable to each other, it sounds like we're saying, where did the rate of change equal one another? Is that correct, or is it like the intersection of two things?
It's a partial rate of change, x, y, and z. So it is a rate of change.
Okay.
But it's partial derivatives, so we have to say partial rate of change, I guess.
Okay. And then let's just solve a system of equations, and then that gives a point.
Yes. Now, the reason that these two things are equal to each other, can you imagine that the places where big things are going to happen and small things are going to happen? In the 3D world, we can still imagine hills, right? Tops of hills and bottoms of valleys. Well, when you're looking at tops of hills and bottoms of valleys, don't you think it's a change of 0?
Right.
So when you set these both things equal to each other, if you move them over to one side, aren't you making the first guy take away the second guy equal to 0? So in a way, aren't you looking for places where rates of change are 0?
Okay.
And it's a difference in rate of change between the two. When it is equal to 0, that's when the interesting things are going to happen. Another way to conceptually look at that, can you imagine that you're only looking at values of x, y, and z for which this is true? And within these values of x, y's, and z's, what's the biggest answer that this can ever be? And what's the smallest answer this could be?
And that's why we moved the 26 over to the left-hand side with everything else?
It's just a way of making it consistent with the normal technique of doing these.
Okay.
Right. Now, I thought, this is your time up. So for those, as I say, I don't want to make you feel that you're obliged to be here if you're good enough at this point. But I'm going to continue for another 20 minutes. So I'll give you a few seconds just to log out and do what you need to do if you have to. I think while that's happening, I will give you a joke, because I really miss an audience, and you are kind of captive. Well, not really. I guess you could put mute on. So here goes. Why do Polish people always buy BMW cars? You meant to say, I don't know.
I don't know.
It's the only ones they know how to spell. No? Okay. Have we, I'm going to move on and do one even more ugly version of this. So we did, you know, FXY version, we've done an FXY version. The third one I want to do is an application question. And they can certainly be challenging, because you have to set up the system of equations before you can even get them done. So where are we? Sorry about all the scanning around. I'm trying to find the one I wanted to do, but evidently, oh God, it's in front of me. Okay, here it goes. This is not a question, but let me talk you through this one. Do you know that you get constraints that aren't equal to 16? They're things like x squared plus y squared has to be less than or equal to 16 or greater than 10, that kind of thing. And you might think, does that make a big difference? And the answer is no, it doesn't. All you will do is the same two steps. The x squared plus y squared less than or equal to 16 is only going to be important when you look at the lambda equals 0 situation. Because you may get a point, and if that point works, which it does in this question here, then you can use it. But when you come to doing the g of x guy, it's still this fella, right? It's still the usual guy. And so when you write it down, I prefer to write things down on the boundary, because to me, it's the same thing as saying x squared plus y squared minus 16 is 0, but that just looks nicer in my brain, that's all. So if this says greater than 16, you'd still make this equal to it. So there's that one. Now, here's the fella. Suppose you have got a question where you're being asked to find the maximum or minimum value of something. The two main questions they've got are, if I remember right, are box, which is this one, and I think the other type is a point in space, and what's the biggest and smallest distance to that point in space. So the question might be, what's the shortest distance between the point 1, 2, 3 and the plane f of xy equals 3x plus 2y, that kind of thing. Right, so the one I've got here, which is what I'm going to talk through, is the kind of grown-up version of the Calc 1 question. Can you remember a Calc 1 question that went and said there was a box with a square base and its volume was something, and what's the maximum volume you could get, that kind of question? This is the kind of grown-up version to it. So it says, use Lagrange multipliers to find the dimensions of a rectangular box with the largest volume. Okay. And we're being asked to do it when we're told that the surface area is 676. So let's see what I do. There's my little box. I like to draw pictures. Now, since we know the surface area, that's going to be the constraint function. There should be an A there. The surface area is this guy. Now, if I call this X, this Y, and this Z, Because in this world, can't the X, Y, and Zs get big and small, totally independent of each other? So this surface area is made of a floor, which is an XY, and a roof, which is an XY. So that's where that came from. If you look at this side wall, its area is YZ, and there's another one down here. So that's where the two YZs and the other one you can imagine being the ceiling and the floor. Now, this function generates the constraint. So we are looking, or we're only allowed to look in places where 2xy plus 2xz plus 2yz is equal to 676. Now, what do we know about the thing that we're trying to maximize? We're trying to maximize the volume, which in this case is just x times y times z. So our question could be phrased as, find the maximum value of the function f subject to this constraint. So once you've created that, you do exactly what we did in all the other stories. So creating the equation, or the equations that generate the maximum value thing, is our first job. So that's done. So I can get that out of the way. So what do I have? I have the function f, and I have a constraint g. There's the gradients equal to each other with the lambda. If you differentiate x, y, z, darn space. Oh, good, I fixed it. Did I fix it? Yes, I did. Equation 1, this guy here should say yz. And he does. So I only made a little typo there, right? That should say yz, but I fixed it here, so we're good. Xz and then xy. So when you match the first, second, and third equations, you get this, and your fourth equation is your constraint. Right, so far so good. Right. The partial derivative of x, the partial derivative of y, the partial derivative of z is being matched up. Now, when you test lambda is 0, you get yz is 0, xz is 0, xy is 0. Those three things can only be 0 at the same time if you make x, y, and z 0. Right? You have to do it to all of them. Now, if you make x, y, and z all zeros, you see it doesn't satisfy that one. So you can't use it, which is kind of the usual way these questions work, is that lambda equals 0 doesn't give you a usable solution. But we have to check it, because you know the first time you don't check it is the first time that you actually get an answer that you can use. So always work on the assumption that that is going to happen. Right, now if you make lambda not equal to 0, you take these two and divide them, and then you take 1 and 3 and divide them. Now if you take these two and divide them, you see how the y and z's give you this fella. If you do a cross multiply, you get this. Distribute it. And for some reason, better known to myself, I just rearranged it there. Now, if you go to that one there, it's kind of bad news. I do have relationships between the variables, but they're not very useful because there's x's, y's, and z's. I can't really get much out of this, but maybe we'll get lucky on this one. Well, if I did this one, you do a little cross multiply, and we get this, which gets you this, which gets me to here. Now, this does contain x, y's, and z's, but it also contains useful result. If you write it like y times z minus x, and we know that has to be 0, then one choice is y equals 0. I'm going to kick that one out. Why is y equals 0 not even worth looking at in this story? If it was 0, wouldn't this side here be 0 units long? What would happen to a box if you made its length or its width 0? It would disappear on you. Well, that's definitely not going to be very likely answer, is it? So that's why I kicked it out. Are we good? We are good. Okay. So, moving on. I now know Z equals X. You see this ugly one that I didn't have much use for? If you plug it into here, you now get this result. X equals 0 is useless, but it now tells me Y equals X. Ah, so if this is going to work, Z has to equal X, Y has to equal X. So doesn't that make X has to equal Y has to equal Z? So they all have to equal each other. So I now can go to the constraint function and replace the Y with an X, replace the Z with an X. We get this, which becomes that, which becomes this. Take the square root, only use the positive because it's a dimension, make it look pretty. And there's the dimensions of your boxes. Is that, I mean, there's a lot in that, but did that make sense? We go? Any questions about that? Because I did go through it relatively quickly. Right, you don't know what you don't know till you try it. So when you go in and you start doing these questions, hopefully you'll have my examples either printed out or beside you, and try and follow the process. The numbers will change and the algebra might be a little bit different. It's bound to be from question to question. But the way you approach it is pretty much the same each time. Try a land equals 0, see what you get. Most of the time you'll get nothing that's usable. Then you can do equation 1 divided by equation 2, equation 1 divided by equation 3. Now, I've decided in the questions I've got to do 1 and 2 and 1 and 3. But if you felt like it, couldn't you do 1 divided by 2 and 2 divided by 3 if you found that those two might interact in a better way, right? Because you can imagine some situations when I look at equation 2 and I look at equation 3 and I say, if I divide them, a lot of things are going to cancel out and it's going to be a quite nice looking thing that will probably allow me to get some relationship, because you're after y is equal to x squared, z is equal to 2y, right? You're after something like that, or even x equals 0, I guess, if you want, but you're looking for something that's going to allow me to eventually restrict the variables in my constraint function to only contain one variable, x, y, or z, whatever it ends up being. Because if you can get that to happen, you can then find one variable. And once you know x, that will let you get y, which will then let you get z. But can you imagine in another situation, it might be easier to do it with z's. So you find the number for z, and then that allows you to get x, and then that allows you to get y. So there's a kind of backwards process. Well, I'm pretty much going to finish now with any questions. You all know about your tests. You all know about how to use Cam Scanner, or you've got your own thing. You all liked my jokes.
I've got a question here.
Go for it.
Do you have any strategy for picking a variable to solve for, or is it just going to be kind of guess and check?
There's no easy way to describe that except by experience, and you've not had a lot of experience because this is the first time you've seen these. Yeah. But when you look at your three equation, let's suppose it was f, x, y, z, right? Because that'll give me three equations and a constraint equation, right? Well, when I look at the first, second, and third, I visually try a little pretend division in my head and say, okay, suppose I took 1 and 2 on the left. Would they play well together? Would they cancel out? Would they become nicer? Or would it just be a really, really ugly fraction? And if I think they're going to look nice, I'll probably use it. And if I think it's going to be a really ugly fraction, I'll probably avoid it. It's easier when there's only an fxy situation because you only have three equations, equation 1 and equation 2. that you have to divide because there's no choices. And equation 3 is going to be a constraint function that gets used at the end anyway. You don't really do anything with a constraint function except use it to check, you know, when lambda is 0, can I use it? And then at the end, the constraint function gets used because the x gets turned into y's or the y's gets turned into x's. Right? So in an fxy world, there is no choice. It's equation 1 divided by equation 2. But in an fxyz function, you have some choices, right? You could say 1 and 3 and 2 and 3, right? You could say 1 and 2 and 1 and 3, right? And I don't know their combinations. I think that's it, right? So I guess you've only got 2 distinct pairings that are going to make sense, right?
Yep.
And a lot of the questions that I've seen, at least, there's an awful lot of symmetry to most of the equations, so it probably won't matter. You end up with the same answer at the end, even if you go a slightly different route. But I haven't seen many questions where equation 3 is really horrible and the other 2 are quite nice. They all tend to be equally ugly or equally nice. Right.
Okay.
Okay, are we good?
Yeah.
Then I'm calling that good for today. Have a nice day, and I'll see you. If you need to see me, you can always do the usual and shoot me an email, and I'll try and help.
All right. Thank you.
Thank you.
Thank you. Have a good day.
Oh, Josh, before you go, Josh Story, you got
Yeah,
a black,
me.
yeah, you got a little dog.
Yeah, I do.
Oh, come on, wait a minute, guys. You can't leave without seeing our dog. Right, yeah. Would you look at that big suck up? What is its name?
Her name's Arrow. I don't know. She's my mom's puppy. I'm just watching it.
Oh, she looks so soft.
She is really soft. She's also a biter.
Oh, is she teething right now because she's a puppy?
Yeah. Mm-hmm.
Right. Can you hear my dog barking in the background?
Yeah, I can.
Right. Do you know why? She saw your dog.
Oh no, I'm sorry.
Oh God. Oh God. Uh-oh. I think your dog can hear my dogs. Okay, bye-bye everyone. Nice seeing you all. I'm out of here.